So I want to talk about already we have seen indicator functions and some situations where indicator functions are used intensely. So this is the section on what is called indicator function, indicators, functions, and matchings. Okay. So if A is an event, recall A is an event, then 1A, sometimes I write IA, I don't know, maybe write IA is the indicator function. So IA of omega is equal to 1 or 0, depending on whether omega is in A, omega not in A. Okay. This is the definition. And so basic property is that, so indicator function of A union B is indicator function of A, excuse me, just one moment. Plus indicator function of B minus indicator function of A intersection B. And yeah, suppose that, so suppose you have A is equal to A1 union A2 union AN, then so probability of A is equal to so sum over, yeah, let us just write this first of all. I think the connection, okay, so this is basic thing, but so this is something that we have used before. You think of indicator function as a random variable, then the expected value of this is precisely the probability of A. Okay. We are working with A being discrete. Sorry, the we are what? Yeah. So yeah. Anyway, this A. So let us just verify this. What is, so XA IA is a discrete random variable. Okay, discrete random variable, and for, so you just apply the definition and you get this. It takes value 1 and 0. So 1 times probability of IA equals 1 plus 0 times probability of IA equals 0. So forget that. So 1 times probability of IA equals 1 is exactly probability of that set is exactly A, because it's indicator function. So this is clear. Okay. So now you may use this to write. So repeated application of this will tell you that this is equal to summation IA1, IA, let me write here IAR, R going from 1 to N, minus summation indicator function. I and sigma look alike. Sorry. So summation I A R intersection AS, and here R less than S. So and so on, and then some plus minus 1 power some n indicated function of intersection of all of these. This is what is called the inclusion exclusion principle. This comes out of writing this set as a disjoint union of certain sets. So let me not elaborate on this. This is, I'm just simply recalling all these things. This is something you can immediately verify. Our repeated application of this, you can use induction to prove this. And this tells us that probability of A is equal to, now just take expectations of the random variables, and expectation is linear. So that also says this. This is what is called inclusion exclusion principle. We have seen this maybe some time ago. If you haven't seen it, this is the AR intersection AS or less than S, and then plus. So summation over probability of exactly 3 of them occurring, AR intersection AS intersection AT, and so on, or less than S less than T, and so on. Okay, plus minus. So this time it's minus, but in general the signs keep alternating, and even number of intersections means I have negative sign, so maybe this is minus sign. There's a minus 1 here, so n minus 1 summation probability of, sorry, yeah, well there's just only one term, so probability of intersection of all of them, intersection A. Okay, now I want to do a problem which involves matchings. So before that, let us just recall. Okay, this is a definition in case you have not seen it before. Permutation, permutation 1 pi of n objects. So this set 1, 2, 3 up to n is called. So you can think of permutation as a bijection, or you can think of it as a sequence. Is called a derangement. If pi I is not equal to I for every I. Okay. Example. So just, okay, very simple. So 3, 1, 2 is a derangement, and also 2, 2, 3, 1. So this is a code for writing. So as a permutation, 1 goes to 3, 3, 2 goes to 1, blah, 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 or derangements. And of course, so you can write anything 4, 2, 3, 1 is not. Okay. So now the question is, count the number of derangements. Of n when objects are n numbers. Derangements of 1 up to n. So problem. So it's a purely combinatorial problem. You can use inclusion exclusion principle and count it and so on. And that's exactly what we are going to do. Let me see. Um, yeah, I want to discuss this. It's a very interesting problem. Okay, so let me. So one approach is so you let AI be the set of permutations. So everything is so when you say permutations, with this set of permutations. Which fixes I. That is, which maps I to I, or I is in its place. So it matches, I matches with I. That's why this word matching is relevant here. Okay. Now, so you compute. So, okay. So the set that is of interest to us is the complement of the set. Okay. A1 union A2 union AN. Okay. So this set equals the complement of the set. Set complement of the set of derangements. So we should just give it a name also, complement of the set. Let us write here Dn of derangements. Okay. So you can write now. So you just, okay, let me write this. What one can either work with cardinality or this one, but let me just say what I have to say. So what is, yeah, so let's just write this inclusion exclusion principle, what it says for this union. This is equal to summation over probability of AR minus summation over probability of AR intersection AS. So here R less than S, and then plus blah blah blah, and then finally as minus 1 power n minus 1 probability of A1 intersection AN. All right, so this is equal to, so now probability of AR, let us just think about what it is. This means that the rth element is in rth place. Okay, rth element is in rth place, and remaining anything can happen. So this happens. So the total number of permutations is n factorial, and here n minus 1 factorial. Now, if you sum over r, and now r going from 1 to n, okay, so exactly n of them. So this is n factorial by n factorial. The next one, yeah. Just 1 second. Let me think about it. Mm. So I want to rewrite it slightly differently. N by n. This may be better. Okay. Summation. The next one, you do likewise. P A R intersection A S. Now R is less than S. So, well, mm, so the value of this probability is going to be independent of the values R and S. Okay. So you can just choose R and S. So two numbers out of 1 to n. So that can be done in n choose 2 ways. And now R has to go to the rth place and S has to go to the sth place. The remaining can happen in any one of the ways. So that is n minus 2 factorial divided by n factorial, probability of that happening. So this is n choose 2. You keep it as n choose 2. And here you write n times n minus 1. Yeah, and so on. And proceed like this. Okay. So you can simplify this, I suppose, slightly. So this is 1 by 2 factorial. So n times n minus 1 by 1 into 2. That's right. Yeah. So on. So let's just do it for one more term. P AR intersection AS intersection AT. And this is equal to exactly n choose 3 times n minus 3 factorial divided by n factorial. So that will simplify to 1 by 3 factorial, right? Okay, and so on. So, okay, that stops. Uh, and now you can see what is the pattern that is emerging. So, yeah, so probability that, so this is just computing what? The probability that at least one of the numbers is in the correct place. So probability that are given, therefore, probability of the derangement happening, that is a typical permutation is a derangement, is the complement of this. So, okay, before I write that, let us plug in these values in the previous equation. So let me just erase this because it will become important to know. So this is probability of whatever I just now said, union AR, or going from 1 up to n. This is equal to, so the first one, you can, n and n cancels, in fact, this is equal to 1. So 1 minus 1 by 2 factorial plus 1 by 3 factorial minus 1 by 4 factorial, like this, and so on. And finally, plus minus 1 power n, maybe it's n minus 1, I think. Okay, n minus 1 and 1 by n factorial. All the numbers are in place, and probability of that happening is exactly 1 by n factorial. Okay. Now, that means that, therefore, probability of a permutation being a derangement is 1 minus this. So that is 1 by 2 factorial minus 1 by 3 factorial plus 1 by 4 factorial minus blah 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 plus minus 1 power n 1 by n factorial. Okay. If you want, you can throw in that +1 and -1. This already means that, yeah, so let us just, yeah. So if we allow, if n goes to infinity, then probability of dn goes to what number? So here you just take sum of all the series, this series alternating 1 by n factorial, and that is exactly 1 by e. So it's a very surprising result. Suddenly this exponential e appears. Okay, so this is an interesting result in itself. But suppose that we are interested to compute. So suppose that let us say Bm, I don't know that, remember the notation. Uh, let me just check with something. 1 second. Ah, so I checked the notation in the book. So SM. Okay, so this already. Okay, let me move further. I think it's not waste time. So you can, what I wanted to say was you can compute the, I probably just, let me, I think it's given as a problem. So I will discuss this later. Okay. We'll talk about that later. At the moment, I'm happy to just demonstrate this. So one other situation where this type of concepts become relevant is the following. So suppose that, so another, this is called networks and their reliability. So suppose that you have a graph that G is a graph. So that means you have vertex set and an edge set. And we consider only simple graphs. So some set of vertices. Okay. And actually you can allow multiple edges also. It doesn't really matter. But let us not allow looping edges. Okay. Something like this. And maybe, and then you just have one more like this, and possibly another directly going here like this. Okay, so you think of these as possible routes from one city to another, or maybe network of railway lines, or airplane connections, or you can think of this as some kind of a circuit board, but always sort of directed graphs. Okay, so let us assume that there is a source and a sink. This is a source. Maybe this is a sink. I don't know. It doesn't really matter. Let us take this. So source and target. And you can think of, there are ever so many models. So some directed graphs. Uh, some edges can be going this way. Another can go this way. It doesn't matter which direction things are oriented. But what becomes relevant is only those which lead from source to target. So if I have an edge like this is not going to appear because it has source different from S. So let us just indicate, we ignore all the edges where there is no path which has that as a thing. So let us write like this. Okay. Let us put like this. Okay. And now, so you have a huge network. The thing is that This is a simple one anyway. So uh, any one particular route may be abstracted or may be available. And suppose that an edge, okay, so this is an edge and it is available with the probability. So the probability that this edge E is available is, let us say, P of E. So now it is like, mathematically speaking, a graph, oriented graph with a source S and target T, and every edge occurs in some path or the other. Only those are going to be relevant for us, so that's the only thing that I have indicated. And then each edge comes with a certain weight, and the weight is a number between 0 and 1. Okay, it's a number between 0 and 1. And so so probability of, let us say, not x, this is better to write xe. Xe indicates xe is edge E is available. Edge E is working. So it is assuming the value 1 if edge E is working, and is assuming the value 0 if E is not working. Okay. So what is the game here? So the thing is, yeah, so a particular path may be available. For it to be available, all the edges that connects here to here, let us say this, let's just, yeah, so this path is available only if, of course, each edge is available. Each edge along that path is available. Okay. And in that case, you can associate the probability of that path. So let us indicate this by P, pi, probability of uh, pi being available. So I write here pi available. Um, Available, pi available, being available, is, of course, then the product of these, all these probabilities, P of E, so edge in, so PE is the weight. Okay. All right. So this is P is the weight, uh, and this is this. Okay. Of course, pi is available. Let us denote that by x pi. X pi is the random variable which says that pi is available, and that's actually equal to product of xe, and E is available. E is along pi. Okay. So this is the thing. And in this, we assume that, of course, you are not backtracking and so on. If you backtrack, well, there is no backtracking allowed because the way I have indicated the arrows, you cannot backtrack because there are arrows. So you think of each one of these as sort of one-way streets, if you like. Okay. And now if you apply the definition, so you see, this is yeah, the basic assumption is that a particular edge, may work or fail to work independently of any other edge working or not working. So that is the basic assumption in this model. This is a very simplified model. So we assume that, so I write, we assume that availability of any edge, availability of any edge is independent of availability of any other edge. availability or working nature, availability of any other edge. Any other. Now, in this case, what is reliability? How is so? Reliability is something that you associate a number. So reliability ability of a network. So network with the prescribed source and sink. Okay, with the source yes and sink or target T is the expectation is the um, expectation or probability. I don't recall, but probably I'll just check that in a minute. Yeah, reliability. We define reliability of a network is the probability that there is a path from this thing using only edges which are working. So that's the thing. Is the probability that there is a path or route or whatever that is available. So the way I use word available is if it is working, yeah. So you may say that a particular path is there, but if it is not working, then I say that path is obstructed and not available. So available, which means and working automatically for me. Okay. Okay. So this is finally going to be therefore a number. This is a number between 0 and 1. And the problem is, suppose I give you, a network is given, how to compute. So you want to compute. So network with this data about X, this probability of any edge working. So yeah, that data also should be given. If we want to compute its reliability. Yeah. Okay. So let us take a simple example. Yeah. So you see, now you have to come. So let us take this network itself. Okay. There are not too many paths. So 1, and then so from here to here it is 2, and from here to here there are 3 paths. So in all there are 6 paths available. Okay, but if I must proceed, I should give them labels and so on. Let us do this 1, 2, 3, 4, 5. Okay, maybe make this 4 and the other one 5. Better that way. So this is 4 and this is 5. Okay, so we just from 1 to 2 there are 2 paths essentially, and then to 5 there are 3 paths. Okay, all right, in between there is something here, but we can just, so essentially there are therefore 6 paths. So 1, So let's not write this as 1 and from S to T. Okay, so everything is going this way. All right. So for each one of the path, it's easy to find the probability that it is not working. You see, the important thing is that, sorry. Yeah, if it is working, then all the things must be in working condition. Um, so whereas if it fails, so if any one of them fails, any one of the edges are not working, then the path will not work. So it's much easier to compute, uh, the failure of this one. So you see, uh, so blue color. So suppose pi is a path, okay, from S to T, okay. So I write a general sentence, then what is, let us, what is this? Think it's pi being away. Sorry, this is pi. No. This one. mm, yeah, I want to. Each one is available. No, this one is not quite right. The way I have written here is not okay. Let us do that first, I think. So pi is a path from S to T. We want to, so let us denote by this symbol zeta pi. This is also used in the book, is a thing that pi is working. So this is a, let me just check what is there in the notation. One, if there is a working thing available, okay, it's a little complicated. Pi is a random variable. Is sorry, just 1 second. Let me see. This is a random variable which is one. Yeah, which is one. Yeah, I need some space. One, if pi is working. It's a very interesting concept, consisting of only elementary things if pi is not working. I think what I said earlier is not quite right. Let us compute what is the probability that uh, pi is working. So you see, because this is it's taking value either 1 or 0. Okay, let us just write this. Probability that this is equal to 1 is what we want to compute. Okay. So, or in other words, even before we compute it, we want to express, that's the main point, express zeta pi in terms of xe. Okay. So, yeah. So if you have a path, let's just simplify that. So E is along this. This is my path pi. Okay. So each one of these should be working in order for this to work. Okay. but that's a little. So how can pi fail? So xc. So if any one of the xc is 0, okay, then pi is not working. Okay, so xc must be 0. So that means that it must be 1 minus xe. This is the random variable which picks up. Now you take product of all these things and ask yourself, when is this? Yeah. Yeah. So this one, let me say this. 1 minus xe. Do I want 1 minus xe or this? Xe must work. All these are working. It must become 0 if one of them is not working. So 1 minus product of all these. So if one of them, so if xe, so what is it that we want to prove? Let me copy that. Sorry, I forgot that. So 1 minus pi not working. This is a complicated formula. Just, yeah. Let us write this carefully. I'm sorry. Z pi is equal to 1 minus. So, so that may be, let's just write here x pi not working. Minus pi not working. X pi not working. What is x pi? Yeah, this is complicated to write. I'm just going to copy from the book and explain. I think that's better indicator function of this not working. 1 minus. Okay, so he's defining not for individual path, but for the whole thing together. Yeah. So okay, this is fine, but let us, so there is one other term that is defined, which is xi of x. So, this is equal to 1 minus product of indicator functions pi not working. Okay, so in other words, you want to think of you see, you have a network and you want, so this is, you want to have this is equal to 1 if there is a path, if X is working. So let me just say that here. What is this? Just once again. Sorry, I should have. So structure function taking values. So let me say this once again. Okay, so here is, let me once again state what is our aim. We want to compute reliability of a network, okay? And that's going to be some number between 0 and 1. You see, the thing is, at any given moment, some edge may work, some edge may not work, and so on. And you have that is why you have these probabilities assigned to each one of them. And at any given moment, you have some situation, and you have, therefore, you can only talk about expectation. You want to express expectation, reliability as an expectation. That's the right thing to say. Okay, reliability as an expectation. Reliability of this thing is of a network with source S and target is a probability that there is a path that is available and working. So this probability is being described in terms of what is called, so the realization. So you have a random variable X, and which assigns, this probability PE corresponding to each edge. Okay, and now what you are doing is, so it's a slightly complicated concept, but let me say what it is. I think I sort of messed up this one, but let me attempt at it once again. So you see, reliability depends on the availability of possible of availability of paths which depend on the probabilities for each edge working probabilities, each edge. Okay, and this is given by some vector PE. Okay, so PE, E in edge. Now, so this, you just think of it as some kind of a vector P, and then you want to compute R of P. Now I introduce, of course, XE, this random variable. All right. Now, for this given probabilities, you associate. So this is called, okay. So X denotes the realization. So this is a word that they use, realization of the network. Okay. So realization is just this collection of various x's and with the available probabilities. So now what you do is you define this xi of x. I was trying to do that without describing this notation x. So xi of x is equal to the indicator function for a given realization. For indicator function for a working path. Okay, given realization for a working path. So I spent too much time on this. So now the which is equal to 1 if x is working. Such a working connection exists. Working connection exists. 0 otherwise. So then realization of P is nothing but, so this is, you can take it as a definition, as expectation of xi of x. And how to describe xi of x? Xi of x, first of all, as a random variable in terms of various x's. So that's our aim. So we just write this in terms of symbols. One, if there is a working connection, correct? So this is nothing but 1 minus product of indicator function of pi not working. Notice that for pi of psi to be 0, this every path which is not working must return the value 1. That is, none of the path is working. Okay, if none of the path is working, then the answer here will be equal to 0. And if at least one path is working, then indicator function that will return 0 here. And that means 1 minus product of this is 0. But I pi, this is what I was saying, indicator function of pi not working. So this pi, for pi not working is equal to so that is what we need to compute. This is product of 1 minus these edges. Product of 1 minus product of xe. Okay, 1 minus, sorry. I wrote xe here. Xe e in pi. Okay. Why so? Because let us just think about it, whether this is pi or. Let us understand this. When will this be 0? If one of the edge is working, right? So when will this be 1? At least one of the edges is not working. So it must be product of xe equals this. So 1 minus product of xe. That is what I wrote first. This is not correct. 1 minus product of xe. Yeah, this I want it to be like this because if one of the edges returns 0, that means this edge is not working, this product will be 0. And therefore, 1 minus product of xe, e in pi, this will return the value 1. So that's why I pi is exactly this. And now you can write therefore psi of this is equal to 1 minus product of each one of these. This product is over pi, 1 minus product of e in pi, and here xe. Such a simple thing, but very confusing to me. Is this clear? We want this to be equal to 1 precisely if pi is not working. And pi not working meaning, well, it must be 1 minus every edge is working. Because if even if one of the edges is not working, this product will be 0. So that this is the thing. And now you can compute what is the reliability. So reliability of given network P. So this P is a vector, remember. Okay. This is expectation of this, expectation of the of x, and this is 1 minus product. Independence is required right now. So 1 minus product. Expectation of this, because it's a Bernoulli distribution each edge. So this is P of E. And here E is in pi. And this is over all possible available paths. All possible paths in the network. So this is the formula for reliability. Okay, so I want to work out some problems involving these concepts. Question 1. So we have a bias coin is tossed many times, n times, and it's given that probability of head is equal to P. Okay, show that the expected number of runs is 1 plus 2 times n minus 1 times P times n minus P. So in these type of problems, you must understand what is the elementary concept or event that is relevant here. So, okay, so the way to think of this, so first of all, what is a run? I think this concept had been defined. So suppose you have something like TTH, THH, TH, and number of runs, okay, expected number of runs. So what is a run? Maximal subsequence, constant subsequences, this way to think of it. TT, so that is one run. H by itself is another run. And then again T, single run. And then HH, and then T and H. Okay, so 1, 2, 3, 4, 5, 6. There are 6 runs. But this way, you are interested to compute what is the expected number of runs when you toss a coin n times, n is some arbitrary number, and you are given that probability of p is head is p. Okay. How do you do this? The thing is, just break it up. Let xi be the random variable that the ith toss yields h. Okay. Now you must express run in terms of the number of runs, expected number of runs. So we give it some name, maybe R or something. How to write number of runs in terms of these elementary things? Well, so if you have two successive things which are the same, it should return the value 0. And if they are different, it should give you the value 1. Okay, in terms of xi, this is equal to summation absolute value xi minus xi plus 1, xi minus 1, and I is equal to 1 to n. Yeah, so maybe I equals 2 to n. Yeah, if n equals 1, there is exactly one run, and this matches. There is no, so may assume n equal to, assume n is bigger than or equal to 2. Okay, so you see, you just check that. It doesn't matter if both. So this will return absolute value of xi minus 1 will return the value 1 precisely if the two things are different. For example, x2 minus x3 in this case will be minus 1. Absolute value will give you 1. You take here 1, 2, 3, 4, 5. x5 minus x6, both are 1, so it is 0. Both are 0, it returns 1. So you see, you can just compute it. This is it. Okay.
Sir?
Yes.
Sir, I think we need to add 1 to this because I think this doesn't count the first run.
First one. Okay. No. Yeah. Sure. Sure. Absolutely. Yeah. Okay. That's right. So the term corresponding to 1, I should put 1 here. Yes. n equals 1, or otherwise give me the 0 as the answer. Absolutely, this is correct. Yeah. I could have said x0 equals 1. Then anyway, this is the correct one. Yeah. Now, what you and another way to do that is if everything is 1, of course, this is going to return 0 for you. That's also is wrong. Okay, now we can compute the expectations rather easily. So you need to compute expectation of xi minus 1 in absolute value. But this is a simple enough problem. You can compute it. And so actually this is because successive tosses are independent, it's enough to compute just this expectation of x1 minus x2. Yeah, absolute value of this. Okay, let me finish this. This is therefore 1 plus whatever. So n minus 1 times. Okay, because all these are going to be the same, irrelevant what the value of I is. So this is expectation of this x1 minus so minus x2 in absolute value. Okay, and you just count this. So this turns out to be okay. So it's a simple problem. I So you just count this. What are the values that it takes? This takes values, absolute value will take value 1 or 0. 1, 0. And when does it take value 1? So this is what is relevant for us. If x1, x2, well, takes a value h, t, okay. So let me just write it. The favorable things, h, t, th. And here, this is tt. Although it is not relevant, I write it hh. Okay. And now this is easy to compute. So probability, so expectation therefore is 1 times probability of this occurring is p times 1 minus p, because this is p and this is 1 minus p, or p and 1 minus p, so 2 times this. Okay, and that explains, yeah, 2 times that appears in here. That's all. There's nothing more. Um, so here is another interesting problem. So I want to do that. Okay. An urn contains n balls, numbered, this time numbered 1 to n. Okay. K balls are removed. Balls are removed at random. Removed without replacement. At random. You can just think that K balls are drawn together. No problem. What is the question there? Score is the sum of the numbers drawn. Okay. Find the expected value. Expected value. The score. So here again, solution. So you just say that let xk, okay, so the k is not a good letter. Xj be the random variable that the jth ball is drawn. And you know it's, yeah, okay. So actually I wanted it to be the indicator function that the jth ball is drawn. That is xj is equal to 1 if jth ball is drawn, 0 otherwise. Okay. Or in fact you can do it either way. Do I want it to be this? j, because my score is going to be sum of these things. Total score, so let us denote that by S. S is equal to, so it will depend on the choice, no. So I'll write here string of numbers. So I, I is a, this notation I will use, I1 less than blah 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 less than in, and this is less than or equal to n, and 1 is less than or equal to this. These are the labels or numbers on the balls drawn. So this k, I'm sorry, ik. So if it is this, the score is xi1. This is I1 plus I2 plus blah blah blah. So this is the random variable or something. I want to write like this. X. Okay. So if your draw is this, then actually this is equal to, so the way I have written, this is just I1 plus I2 plus IK. Okay. Right. So this is nothing but, so actually this xj also is defined on the space of all i's. So I may write like this, and this jth ball is drawn, meaning one of the term is exactly j. So this is same thing as I1 plus, so s is the random variable. This is the best way to write it. Therefore s is equal to this. And what you need is expectation of s. But that same thing as expectation of xi1 plus blah 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 plus expectation of xik. But expectation of xj is easy to compute. You see, this is just the indicator function multiplied by a certain number j, that's all. So j, and what is the, so j times something plus 0 times something. So you are drawing k balls, and out of this jth one is drawn. So that can happen in how many ways? Okay. So so jth one, yeah, that is so out of your k, this j one must have occurred, and then for the remaining it can be anything. So this k by k. Remaining I can have n minus 1 factorial, right? Sorry, remaining will be n minus 1. How many choices for the remaining one? That's n minus, sorry, so n minus 1 choose k minus 1 divided by n choose k. You see, this j must have come out of, so there are k choices. Out of the k, one of them must be j. Okay, so this I think is actually, I want, is actually choosing, because I have already chosen my j. J is not there. N minus 1. You are actually making, j is already chosen. Remaining k minus 1 comes out of n minus 1 choices. Total number of choices, it's just blind to any choice you have made and choose k. So this is the this is the expectation, therefore. This is the probability that one of the chosen one is j, okay, times j is this one. So this can be simplified and you compute it. And in fact, this E of S is equal to, so it's just a matter of simplification. We have already done it. Each one of them is the same number. So summation I1 plus blah 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 plus IK, that is this one, times, so sum over this I, okay, times this same number n minus 1, choose k minus. There may be a simpler way to do this, but this is the way I thought of doing it. And now this is summing over all possible choices for this. There are how many? And now for a fixed one, so this is, you see, you simplify this because you can rewrite the sum, right? So this is, yeah, let me say this quickly. So this turns out to be, I don't know. So if you fix an I, okay, how many ways, in how many permutations, how many choices it will appear? So this will, I1 will appear in how many choices, permutations? How many strings like this? Okay, so you are looking at summing over all possible strings in which I1 occurs. Okay, so you fix I1, and if you knock off I1, how many are there? That will be so total number is actually n choose k. Here there are totally n choose k of them, of which having fixed my I1, n minus 1 choose n minus 1 choose k minus 1 are remaining. So you see, there are n minus 1 choose k minus 1 times this one is appearing, this I1 is appearing. And I can just do this for each one of these because that's this factor is independent of this. And when I add up, so just simplify this a little. So there are k terms all with the same factor, but each I1 I am adding that many times. So essentially I am adding all the numbers. So sum over I1 k times n minus 1 choose k minus 1, and here this I1 can be anything from 1 to n, and times this probability. So I got this thing n minus, maybe I left out something, I don't know, n choose k. You try to complete this. So you see, you get it k times, this is sum over all possible numbers 1 up to n. So that is n times n plus 1 by 2. And this n minus 1 by, I seem to have got it twice, I don't know. This may have to be checked. So simplify this, n minus 1 by k minus, so n minus 1 factorial by k minus 1 factorial times n minus k factorial. I seem to be getting this twice, so I'm not sure if this is correct. Check this. So n minus k factorial times k factorial appears in the numerator. Now I'm writing this one, n factorial in the denominator. And you can simplify this a little. So this n and this n factor, n minus 1 factorial cancels with this one. And I have this n minus k factorial goes with cancels with this one. So I seem to be getting k square, but so yeah, not sure if this there is a k factorial here and there is a k minus 1 factorial here. So I seem to be getting a k square here actually. K square times n plus 1 by 2, but I'm not sure if this is correct. There is also this factor. So you try to complete this. Let us, you can take this as, try and do it at home, remaining part of it. Sorry, I may have missed some calculation here. So please complete this. This is an exercise for you to complete this and check. I think, I'm sure I missed out on factor here. Please check. That's all for today. Sorry, I had to stop. Already exceeded time limit.
Thank you, sir.